Building an embodied AI agent that can continuously explore, plan, and develop new skills over long horizons remains a primary challenge in machine learning. Learning in an open environment involves taking an acquired skill, committing it to memory, and using it as a foundation for the next complex capability. Standard language model agents like AutoGPT or React struggle with this accumulation because they are episodic. They execute a plan for a specific prompt, but once that task is over, the context is cleared. They start every new problem from zero. Here is how Voyager addresses this limitation. On the left, traditional agents discard their context after a task. On the right, Voyager connects the LLM to an ever-growing database of verified skills. It achieves lifelong learning entirely through prompting. Delta theta equals 0. To test an agent capable of this type of self-driven growth, researchers chose an environment without a predefined end goal or a fixed storyline. Minecraft serves as a laboratory for this. It offers a procedurally generated sandbox where the agent gathers resources and invents its own objectives to survive. Progress here is measured by a compositional tech tree. Moving from wood to stone and eventually to iron and diamond requires the agent to chain together increasingly difficult extraction and crafting skills. We are going to engineer Voyager from scratch by building out its 3 foundational modules: the action space, the curriculum, and the memory library. This architecture shifts the focus from planning within a single, isolated vacuum to banking and compounding knowledge over a lifetime of interaction. The first engineering constraint is the interface. We have a frozen LLM, and we need it to physically interact with a 3D environment without using a reinforcement learning policy. Traditional reinforcement learning typically maps environmental states to low-level motor torques. Voyager instead uses code generation as its primary action space. This illustrates the translation layer. Instead of continuous motor commands, the processor generates structured programs, like a JavaScript function to craft a stone shovel. That code interfaces with the text state via the high-level MindFlayer API, handling the physics to execute the instructions. Using code as the action space avoids the problem of catastrophic forgetting. While neural network weights are easily corrupted during retraining, verified JavaScript is a stable, immutable asset. This also enables composition. When the agent needs to perform a long-horizon task, it can write a high-level function that calls several previously verified programs as subroutines. By treating code as the action space, we extract the learning process from the model's weights, allowing the agent's capabilities to be preserved and combined through standard software engineering. But having an action space doesn't explain motivation. Without a human providing a prompt or a hard-coded reward function, how does the agent decide what to do next? This is handled by the first major architectural module, the automatic curriculum. The curriculum block ingests 4 real-time data streams: the agent's inventory, the surrounding biome, health status, and previously completed or failed tasks. It processes these to find a goal that maximizes diversity within the agent's limits, essentially an in-context novelty search. Because the system is stay-aware, it generates tasks from the bottom up. It won't suggest mining for iron if the agent is in a desert without the necessary tools. The data shows how vital this self-calibration is. Replacing this automatic module with a random task generator led to a 93% drop in discovered items, as the agent attempted goals it wasn't yet equipped to handle. This dynamic mechanism allows the agent to navigate an open world by continuously proposing its own difficulty-calibrated tasks. Even with a clear goal, LLMs rarely produce perfect, functional action code on the first attempt. Voyager bridges the gap between a raw prompt and a working skill through the iterative prompting loop. This shows the refinement cycle. The program writer generates JavaScript, runs it in the environment, and receives text feedback to fix mistakes. That feedback flows through 3 rails: environment feedback, execution errors, and a self-verification check. Self-verification is the core of the loop. A secondary GPT-4 agent acts as a critic, evaluating the resulting state of the world to judge whether the program actually succeeded. This check is necessary for progress. Removing the self-verification critic causes a 73% drop in item discovery because the agent loses the ability to distinguish between successful code and a failure that looks correct. To prevent infinite loops, the system uses a 4-round escape hatch. If the agent can't solve a task after 4 attempts, it abandons the objective and asks the curriculum for a new, perhaps simpler task. This integrated critic provides the honest termination signal required for the agent to autonomously refine its own behavior. Once a piece of code is verified and the task is complete, how is that knowledge stored for later use? It is committed to the final module, the ever-growing skill library. The storage architecture uses a vector database. GPT 3.5 writes a description of the code, and an embedding of that description serves as the database key. The database value is the executable JavaScript program itself. When the curriculum proposes a new task, Voyager retrieves the top 5 most relevant historical skills from this library and includes them in the next prompt as in-context examples. Without this library, the agent's progress plateaus. It is forced to regenerate code for common tasks like crafting or mining every time they occur, rather than retrieving and reusing a verified solution. Indexing discrete functions in an external vector space provides a scalable template for transforming an episodic agent into a lifelong learner. These modules function as a single continuous loop. The curriculum proposes a goal, the library provides relevant subskills, and the prompting loop refines the code until it is verified and banked. Compared to baselines like AutoGPT and React, Voyager discovers 3.3 times more unique items and travels 2.3 times further across the map. The impact of this compounding memory is visible in the tech tree speed. Voyager reaches the wood level 15.3 times faster than its counterparts, and it is the only method in the study to successfully unlock the diamond level. This library is also highly portable. Because the skills are just files of JavaScript code, they can be transferred between different agents. In a zero-shot generalization test, researchers took Voyager's populated library and handed it to a standard AutoGPT baseline. Simply having those verified skills allowed the baseline to solve tasks it previously couldn't. There are, however, significant trade-offs. The system's success depends on the code generation quality of GPT-4, which is roughly 15 times more expensive per call than GPT 3.5. The agent still encounters hallucinations. The curriculum sometimes suggests non-existent items like copper swords, and the model occasionally tries to use invalid materials as furnace fuel. Because Voyager relies on text-state APIs, it lacks visual perception or sensory motor control. Any deployment to physical robotics would require additional safety constraints and a bridge to real-world visual data. Voyager demonstrates that building compounding autonomous agents can be achieved through externalized memory and software architecture, bypassing the need for continuous model training.